Centrifugal pump, and today we would like to discuss about flow velocity. As you know, flow velocity is the theoretical velocity that comes in and comes out from the centrifugal pump, and it can be calculated as Vf equal flow rate over area, and it can be written as Q over pi dB, which is Q is flow rate in the pump, D is diameter of blade, and B is the width of blade. And because we have diameter and blade width here, so please make sure that when you calculate the velocity of flow at inlet, Vf1 here, you will use diameter 1 and width of 1. And the equation will become Q over pi d1 b1. And if you calculated flow velocity at outlet, so the equation will become Q over pi d2 b2. And here I would like to give you a detailed calculation about flow velocity, because we will have two conditions of blade design. For example, if we have a impeller and shroud like this, we must know that the width of blade is this area. The distance of this is determined as width of blade. So why we calculated Vf2 is equal to Q over pi d2 b2, because we imagine that the water will flow like a source. Mean from one source here, the water will flow radially like this. And then because the tip here, it will create a very thin area at the exit here, so means that the area that water flows out is actually 2 pi r, the parameter of this impeller, times the height of this one. So it will become 2 pi r times width of blade, or we could write pi d, means the parameter of the impeller here, and b here is the width of this impeller. So the pi d and b will give us the area of this section, because water will flow out through this area. And because the tips here is very thin, so we could calculate that the area is pi d and b, because the area is very thin, and we assume that water could flow throughout this area. So please remember that the equation of Vf2 equal Q pi d2 b2 is actually valid for a blade that have a very thin thickness at the outlet here. And then what happens if our blade have thickness here? So as you could see here, if the blade is thick like this, so means that if we calculate the diameter here, pi d, it will not reflect the area that water flows out, because water did not flow at this area. So somehow we must deduct the area of pi r, 2 pi r here, with the area of the thickness of the blade. So the equation of Vf2 need to be modified, and it becomes Vf2 equal Q over K pi d2 b2, where the K here is the area coefficient. The K here will show how many percent of the area that actually flows the water out. So if the thickness of the outlet blade is 15% from the total outlet area, the area coefficient is 0.85. Then the Vf2 equation will becomes Vf2 equal Q over K pi d2 b2, and K here. It is means that only 85% water. And then if we go to a situation where the thickness here, the thickness of blade here at the outlet is very, very thin, so we could use the same equation, Vf equal Q pi d2b2, and here the K is equal to 1.0 or 100%, because the area here is 100% will flows by water. Sometimes we will use the area coefficient in the inlet. So please be careful with the question whether they give you value of K for inlet and outlet, or they just give you the value of K for the outlet only.